All right, good day. So you're welcome to this week's class of HPHY 309, Introduction to Quantum Physics. The topics we'll treat in this course are the Schrödinger equation, physical interpretation of the wave function as a probability amplitude, uncertainty principle, energy levels and stationary states, solution of the Schrödinger equation in simple one-dimensional cases, solution of the Schrödinger equation for a harmonic oscillator is also a one-dimensional case, then the hydrogen atom. The recommended textbooks are Quantum Mechanics by Mahesh Jain, Quantum Mechanics by Walter Greiner. They are all introductory books on quantum mechanics concepts and applications by Zetili. So these are the recommended books. I think the simplest among the three is the first one. So if this is the first time of taking a quantum physics course, so then the first textbook is for you. So it's the simplest among the three books listed here. Okay, so in introduction, so this is an introductory class, so we'll give so the class will be very, very short, so it's just to introduce the course. So in quantum mechanics, the information about the state of a particle is described by the wave function. So in quantum mechanics, so the information about the state of a particle is described by the wave function. The wave function, we often denote it as psi of x, t in one dimension. Okay, we'll start with one-dimensional case. So x is the position and t is the time. So, and the equation that describes the time evolution is called the Schrödinger equation. The Schrödinger equation. So this is the wave function. Okay. So, and the equation that describes the time evolution is what we call the Schrödinger equation. The Schrödinger equation. Okay. Now, what is the Schrödinger equation? So, so if we have a particle of mass m, that is subject to, so the mass of the particle is m, and the particle is subject to a potential, a one-dimensional potential. Potential is V, that depends on the position and time. Okay, so the Schrödinger wave equation is a partial differential equation. So it can be, the time-dependent form can be written as RH bar, that is psi, that is t. So and the wave function depends on x and t. Equals minus h bar squared over 2m, that is square psi, depending on x and t as well, that x squared plus the potential. Okay, so this is the time-dependent Schrödinger equation. So this equation actually is the energy multiplied by the wave function equals the Hamiltonian multiplied by the wave function. So the Hamiltonian is the kinetic energy plus potential energy. So the potential energy here is V, and the kinetic energy here is minus h bar square over 2m di x squared di x squared. So that is the kinetic energy. Because why is that? Because the kinetic energy is half mv square, where m is the mass of the particle and v is the speed, and it can be written as p square over 2m. So p is the momentum. Okay, momentum of the particle. So this momentum is the product of mass and the velocity. The product of mass and velocity. So this equation can be written in this form. Now in quantum mechanics, the momentum and even the position, they are operators. They are what? They are operators. So, and the square of the momentum, which is the operator in this case, the p squared, is minus h bar squared die squared, die x squared. Okay, and this energy is also an operator. So this energy E is IH bar die it is an operator. Okay, so the energy is an operator. The momentum is also an operator, and the square of the momentum is the square of the momentum operator is given as minus h bar square die x square. So the Schrodinger equation can just be written as the energy multiplied by the acting on the wave function and the Hamiltonian acting on the wave function. So the energy is an operator, is IH by die dt. H is the Hamiltonian, so H is the Hamiltonian, and it's a sum of the kinetic energy and potential energy. So this is let me label this as question 1. So this is time dependent form of the Schrodinger equation in one dimension. So we call psi the wave function and V the potential. So the wave function, the psi, depending on the position x and time t, so contains information about where the particle is located. And we'll talk at the probability density later, but the square of the wave function, the modulo square of the wave function, gives the probability density. Okay, we'll talk about the probability density probably in the next lecture. So this is just to introduce the course to you. Now, the wave function, okay, is psi. There are some properties that a wave function must satisfy before we can say it's a valid wave function. Okay, so let me write properties of a valid wave function. So number 1, let me just write it in the next page. Okay, it's okay. So number 1 is that it must be single valued. The wave function which is psi, must be single valued. It must be continuous. And it must be differentiable. It must be differentiable. Then it must be square integrable. It must be square integrable. What do we mean by square integrable? Square integrable means that if you find the integration of the modulo square of the wave function, okay, modulo square of the wave function, let's say dx, from the whole space that we are given, maybe minus infinity to infinity or 0 to infinity, or the whole space of the position x, it must be less than infinity. So if you integrate the modulo square of the wave function and it is equal to infinity, it means it is not square integrable. If it's less than infinity, then it is square integrable. So let me use this simple example to illustrate that. So the example is that let two functions, let's call the first function psi and the second function phi, let them be defined in the region 0 less than x less than infinity. Then the question is that explain why for the psi of x, which equals to x, cannot be a valid wave function. But the phi of x, which is exponential minus x squared, is could be a valid wave function. Could be a valid wave function. So hint, the integral from 0 to infinity of exponential minus z squared dz equals square root of pi divided by 2. So this is the hint. Alright. Now, so we have to check the two wave functions for these conditions. Okay, it must be single valued. So let's look at the first case. That is psi of x equals x. So this is single valued. In fact, we can plot a graph of, let me plot a graph of the function. Okay, so let's say we create a function for psi. It depends on x and it returns x. Okay, and we plot, so import matplotlib.pyplot as plt. So we can plot, so from numpy import in space. So let's say the x values are from maybe 0 to infinity, but let's use a large number. Let's just 1000. Then plt, so let's plot it. Plt, let's plot x, then psi of x. Okay, so if you plot this, so we can see that the values are continuous, they are single valued, the wave function is single valued. Okay, so this is the wave function, this is the horizontal axis, the x values. So the first part, psi of x equals x, satisfies the first three conditions. It is differentiable. We can differentiate psi of x equals x. Then the last condition to check is that, is this square integrable? So to check if it is square integrable, what we do is we check this integral. So let me call this equation 2. Now, so in our case, we need integral. The range of values of x is from 0 to infinity. So 0 to infinity, then modulo psi squared dx. But in our case, so modulo psi squared is just x squared because x is real. So x squared dx. And if we integrate this, we have x cubed over 3 from 0 to infinity. So, and this will give us infinity. So it means it is not, oh sorry, so let me say the wave function psi of x equals x is not square integrable. It's not square integrable because modulo integral this modulo x squared dx equals infinity. Okay, so therefore it is not a valid, it cannot be a valid wave function. It cannot be a valid wave function. Okay, now let's check the second case. The second case, we are given phi of x equals exponential minus, I think x squared. Yeah, x squared. Now again, we can plot the graph for this. So let's plot the graph. So let's say def. So phi depending on x as well. Then return exponential minus, I think x squared. Yeah. Let me check again. So exponential minus x squared. All right. So Okay, we have to import exp. So from numpy import exp. Then we can plot again. So plt.plot x, then phi of x, plt.show. Okay, you can see it quickly decays to 0. So I think probably the x values are too large. So let me choose another x equals namespace. So that's 0 to maybe 100. Okay, so it decays quickly to 0. Let me check 20. Yeah. So anyway, so it decays quickly to 0. So and it is continuous, and it is also differentiable, and it has single value. It is single valued. Okay, so it satisfies the first 3 criteria. Then the last one, we have to check if it is square integrable. So if it is square integrable, then the integral 0 to infinity of modulo phi of x squared dx must be less than infinity. So in this case, we have phi of x is exponential minus x squared. Then if you square that, dx, and you can write it as integral 0 to infinity exponential minus 2x squared dx. Okay, so this integration can easily be done if we use this standard integral. So exponential. So we are told that we will use the standard integral 0 to infinity of exponential minus z squared dz equals to pi over 2. Now, so but if you compare these two, so this and this, okay, so you can see that 2x squared, so you can say 2x squared equals z squared. Okay, so this 2x squared is equivalent to z squared. Then what will be x? So x squared will be z squared over 2. Then x will be square root of z divided by 2. Then, so it means anywhere we see 2x squared, we replace it by z squared. Anywhere we see x, we replace it by root z over 2. What about dx? So dx, dz will be, so if you differentiate, oh sorry, this 2x squared equals z squared. So I think there's a mistake here. So because x squared, if 2x squared is, so x squared will be z squared over 2. Then x will be square root of z squared is z. Then over square root of 2. Yeah. So it is z over square root of 2. Then dx, dz will be dz over square root of 2. So it means what we do here, this integration, this integral 0 to infinity exponential minus 2x squared dx will be transformed to integral 0 to infinity. The limit of integration will not change, since this is when x is 0, z is 0. When x is infinity, z is infinity. So there's no change in the limit of integration. Then exponential minus, so instead of 2z squared, we replace it by z squared. 2x squared. Then dx is dz divided by square root of 2. So you can say 1 over root 2. So this will be 1 over root 2. Now this integral is what we are given. We are told that it is square root of pi divided by 2. Okay, and this can be written as square root of pi divided by square root of 2 times 4. So that will be square root of 8. So therefore, the integral 0 to infinity exponential minus 2x squared dx equals square root of pi over 8. And the fact is, it is less than infinity. Okay, so therefore, the function phi of x equals exponential minus x squared could be a valid wave function, Okay. All right. So I think we can stop here for today. So since this is an introductory class, so we'll stop here today. So continue in the next class. All right. See you later.